Our understanding of pinch-off saturation in MOSFET is contingent upon a depletion region with infinite resistivity. So when we looked at saturation in pinch-off, this was the situation. The reason we had a saturating current is because the profile of voltage and thus the profile of velocity throughout the channel refuses to be different from the profile of voltage and velocity in pinch-off, because also the profile of charge concentration is the same through the channel as it was in pinch-off. And therefore, for any VDS greater than VDS sat, the distribution of charge is the same as the distribution of charge at VDS equals VDS sat. The distribution of velocity is the same as the distribution of velocity for VDS equal VDS sat. Thus, their product is the same and is equal to I sat, which is why current remains at the same level for any value of VDS above VDS sat. We saw that the balance of VDS, which is any VDS in excess of VDS sat, is going to fall entirely upon the small depletion point that forms between the drain and the end of the channel. So this small depletion point is going to handle every single excess voltage above VDS sat. And the reason that that has to happen is because this depletion region has a conductivity of null. The current density flowing into this depletion region is equal to conductivity times electric field. Thus, the only way that we could have J sat, which is the current flowing through the channel, entering and exiting from the depletion region, is for the electric field to be infinite. And the electric field is going to be infinite if we see a delta V on the depletion point divided by 0. Thus, the width of the depletion point has to be null, and we have to see a finite voltage drop upon it. That finite voltage drop is VDS minus VDS sat. We said that if we try to divide the excess potential between the channel and the depletion point, we will see that the point at which the channel pinches off moves closer to the source. This will mean that the depletion region now has a finite delta X instead of a 0 delta X. This will cause it to have a finite electric field. The finite electric field is not going to be able to move charges across the depletion region with its 0 conductivity. There's a couple of major problems with this argument. First of all, sigma depletion, the conductivity of the depletion region, is not actually null. It's a small conductivity when compared with doped silicon, but it's actually very reasonable. If we look at the band diagram of the MOS capacitor in depletion mode, we will find that we say that the channel is depleted when E Fermi coincides with E Fermi intrinsic. And so we're actually talking more about sigma intrinsic in this case. We're talking about a conductivity in the order of intrinsic silicon, which is not such a low conductivity. It's not actually even equal to the conductivity of silicon dioxide, and it is far from 0. It is small, but it is far from 0. And so when we look at J is going to be equal to sigma depletion, which is non-zero, multiplied by the electric field. And now we want this J, the electric field, we want the current density exiting the channel, J sat, to be equal to J in the depletion zone, to be equal to sigma depletion multiplied by the electric field. So because we have sigma depletion being a finite non-zero quantity, this allows us to get a value for the required electric field across the depletion zone equals to J sat over sigma depletion. And this is going to be a high value, but it's going to be a finite value. Normally, we would think of sigma depletion as 0, and thus this electric field is infinite. But now we know that it is just a high value. So E, the electric field across the depletion region, is going to be equal to delta V across the depletion region divided by delta X. So the only way for this electric field to be a finite number is for delta X to be also a finite number. So when we think about it, if this is the depletion point, and we increase VDS above VDS sat, the only way we could actually maintain the same current that is flowing in the channel is for the depletion point to become a depletion zone with a finite delta X. The more VDS we add, the more delta X we have. And so we can see this in this band diagram. So we have here VDS, which is the drain to source potential, and we have a depletion zone of a certain width. And this depletion zone is going to increase in width as we apply more VDS. So in this case, we have VDS sat, and so the depletion zone starts and ends at the drain. We increase VDS to VDS2, which is above VDS sat, and then we have a depletion region that extends through this. And this is delta V, which is equal to VDS2 minus VDS sat. And thus, this is the point at which we see VDS sat, and this is the start of the depletion zone. And this is delta X2, and delta V over delta X2 is going to give us a value of electric field, which will allow us to drive the current that exits from the channel at this point. The more VDS, the wider the depletion region. Now, what effect is this going to have on the saturation current? If we try to draw the saturation current with a depletion zone that is infinitely resistive, or whose conductivity is 0, we will get the IDS VDS curve with a perfectly saturated current. However, if we have some depletion zone conductivity, we will see current increasing in the saturation region. Now, I'm drawing this with an exaggerated slope because current will increase, but it will increase very slowly. So why is the current increasing here? Because we squeeze both the charge profile and the energy band diagram as we increase the potential across the channel. When we squeeze them, we cause the slopes seen on the energy diagram to increase, which causes us to see more and more velocity. This more velocity multiplied by the same levels of charge is going to give us more current. And the way to model this is to say that saturation current is now not only K over 2 into VGS minus V threshold square, but also to introduce some dependence on VDS. And this is through a constant lambda whose value is volt minus 1, and it's called the channel length modulation constant, because this whole effect is called channel length modulation. So in a transistor with a very large channel length modulation is going to occur primarily because of this effect, because of the finite conductivity of the depletion zone. It is important to notice, though, that in modern transistors, in realistic transistors, channel length modulation is a much more complicated effect, and it happens due to many more factors than just this. It is very well pronounced, and it is usually only characterized by empirical methods rather than by derivations such as the one we did right now. So to summarize, we have a device called the NMOS. N refers for the fact that electrons are the main charge carriers in the channel. When it has 4 terminals, a drain, a source, a gate, and a body. When we apply a gate to source potential less than a certain value called V threshold, it is in a region called cutoff, and its current is equal to 0. When we apply a gate to source potential greater than this V threshold, it is on. If the drain potential is low enough so that the channel has not pinched off, it is in a region called ohmic, and if the drain potential is higher than this pinch-off value, then it is in saturation. In ohmic, the current is a function of drain potential, gain potential, and source potential, whereas in saturation, the current is only a function of gate and source potentials.